is this idea of an atom's electronegativity. All right, so electronegativity is often abbreviated EN, and we can define it as the pull an atom has on the electrons that are shared in a covalent bond. So in other words, the higher the electronegativity, the stronger the pull on those electrons. Right, so you can think of it as sort of the strength that an atom has when it's sharing electrons. How strongly is it pulling on those electrons? The higher the electronegativity, the stronger it is pulling on those shared electrons. On the periodic table, there's a trend that we're going to see, just like we saw in the last chapter. There were several trends in the periodic table. The trend for electronegativity in the periodic table is electronegativity increases from left to right across the table, and it also increases from bottom to top. In a group. So as you go up, it increases. As you go from left to right, it increases as well. All right, and your textbook has an example of this. It tells you the direction in which the electronegativities change. You do not need to memorize electronegativity values. Okay, do not. But you should know the trend. Right? So I will never ask you to tell me what the electronegativity of bromine is. Right? I will give that to you if you need it. You have to be able to use it on a particular example. All right, so you'll notice here, the thing with the highest electronegativity is what? Fluorine. Right, 4.0 is considered the highest electronegativity, and then it goes all the way back to 0. So the electronegativity values go from 0 to 4.0. Right, fluorine is the most electronegative element there is. So how does the electronegativity come into play when we start looking at electrons that are being shared? So we'll take a look at a particular bond and establish that. So we talked about a covalent bond being electrons, being made up of electrons that are shared. If we look at the hydrogen bond in H2, we can now use that information to say a little bit something more about that particular bond. So if I look up the electronegativity for hydrogen, I see that it is 2.1. What's the electronegativity of the other hydrogen? It's also going to be 2. It's the exact same thing, right? It's your 2 H's. So what we're going to be looking at is the difference in the electronegativity. What's the difference in electronegativity between the H and the other H? How do you get the difference? You subtract, right? Big number minus the smaller number. The difference here is 0. There's no difference in electronegativity. So what that means is those electrons here are being pulled equally. Right? The electronegativity value is an indication of the strength of that pull that each of those atoms has on those electrons. So they're being pulled equally in both directions. So that means, right, the electrons are shared equally. So this bond then is called a non-polar covalent bond, right? And in a non-polar covalent bond, we're going to see that our electrons are going to be shared equally. We can calculate that when there's a small difference in electronegativity between the elements or between the atoms that are sharing those electrons. All right, and the range that we're going to use here is anywhere between 0 to 0.4. So you have to look up the electronegativity values, get the difference, and if you find that the difference is relatively small, we're going to say that those electrons are shared equally. So that bond is going to be a non-polar covalent bond. Right? So you will obviously have non-polar bonds between two atoms that are the same, right? Because the difference here is going to be 0. But sometimes you have different elements that have different electronegativities. If the electronegativities are relatively close to each other, those electrons are still going to be roughly evenly shared. When there's a bigger difference in electronegativity, we end up with what's known as a polar covalent bond. Right? So here there is a moderate difference in electronegativity between the elements that are sharing those electrons. All right, and the range here is 0.5 to 1.8. If you look, this is what your textbook uses. If you look at other textbooks, you'll see slightly different ranges, but we're going to use what your textbook is giving us, right? So if the difference in electronegativity between two atoms that are sharing electrons is in this range, we're going to call that bond a polar covalent bond. So for example, right, if we go back up to the one that was on here, we had H and we had Cl. All right, if you were to draw the Lewis, whoops, I'm sorry for the scrolling. If we had something like H and Cl, right, that's the Lewis dot structure for hydrogen chloride. We can look up the electronegativities. Hydrogen is 2.1 and chlorine is 3.0. So the difference in electronegativity, big number minus smaller number, is 0.9. Right? So this bond here, right, is going to be a polar covalent bond because it happens to be in that range. So that means the electrons that are being shared here are not being shared equally. Because the chlorine has a higher electronegativity, it's actually pulling on those electrons more than the H is. So these electrons are actually spending more time around the Cl than they are around the H. So if you were to draw a little electron cloud, right, the cloud would be bigger around the Cl than they are around the H. Just because of the difference in strength on the pull of those electrons. So what that is going to result in, right, if we draw again our HCl over here, right, our electrons are spending more time around the Cl than they are around the H. Electrons have what charge again? Negative, right? So you have your negative electrons spending way more time around the Cl than they are around the H. So that would mean that the Cl end of the molecule is going to have a slight negative charge. And the way that we represent that is by using this symbol. It looks like an S. Just close the tail of it. We put a negative sign. right? This here is the Greek symbol delta. We call it delta minus. And this here means small or slight. Right? It's not a full negative charge, it's not a full positive charge. So delta minus means that the Cl end of the molecule is slightly negative. What do you think is going to happen on the H end of the molecule? It's going to be slightly positive. So we end up with a molecule that has a negative end and a positive end. We can represent that using an arrow that points towards the more electronegative element, like so. And if you notice what I also did, let me redraw that. This arrow here points towards the more electronegative element. The tail end of the arrow, I put a little tick mark next, so it kind of looks like a positive sign, right? So the tail end of the arrow here is a positive end of the molecule, and the arrow points towards the negative end of the molecule. We call this a dipole. Right? Two poles, negative pole, positive pole, due to the difference in electronegativity between those two elements. Right? And you're going to have a dipole in a polar covalent bond. Polar covalent bonds result when there's a moderate difference in electronegativity between 0.5 and 1.8. If the difference in electronegativity is large, right, then we end up with one atom completely ripping the electrons away, right? Their electronegativity is so big that they pull on the electrons and they just take them for themselves. So the electrons are taken completely away. We end up then with charged species, which are our ions, and that's where we end up with our ionic bond, right? So in an ionic bond, the difference in electronegativity has to be really, really big. So above 1.8 is typically what you're going to see. And as we saw last week, right, your ionic bonds are usually formed between what two types of elements? Metals and non-metals, right? Metals are on the left side, where the electronegativity is really low. And the non-metals are on the right side, where the electronegativity is really high. So there is going to be a much bigger difference in electronegativity between your metals and your non-metals, which explains why you have ionic bonds and not the sharing of electrons, right? You don't have covalent bonds between a metal and a non-metal. All right, so table 614 in your book summarizes that relationship of the electronegativity differences between the atoms and the type of bond that results. Right, so small difference in electronegativity, non-polar bond, electrons are shared equally. We have a moderate difference in electronegativity, we've got a polar covalent bond, unequal sharing of electrons. Then we have a large difference in electronegativity. That's our ionic bond. Right? Electrons are not shared, they're going to be transferred because of that huge difference. All right, so we'll jump into now our shapes of the molecules that we're going to encounter. So we've been sort of building layers upon layers up to this point. We've looked at how we use our Lewis symbol to draw our Lewis structure. We've addressed the fact that different elements have different electronegativities, which will affect the nature of the connection or the nature of the bond between your nonmetals. Now we're going to put all of those together to see how those things actually affect the shape of the molecule, but also the polarity of the molecule. So the first thing we're going to address here is the shape. And when it comes to shape, there's a theory in chemistry that we use to predict the shapes of molecules known as VSEPR, which stands for valence shell electron pair repulsion. theory. Right? I know it's not spelled that way, but sometimes it's pronounced VSEPR theory. Instead of saying the whole word, valence shell electron pair, we just say VSEPR theory. Right? So the basis for VSEPR theory is as follows. It says that groups of electrons and a group of electrons for our purpose here can be a lone pair. It can be a single bond. It can be a double bond. Or it can be a triple bond. Want to be as far apart as possible from each other in order to minimize the repulsions between them. And this will then dictate the shape of the molecule. All right, so the basis for VSEPR theory is you have these groups of electrons that want to be as far apart from each other as possible. Right? And that drives what the molecule will actually look like in the end. All right, so we'll start with some simple molecules and then build up a little bit of complexity. So let's say that we had H2, right? So you probably remember what the Lewis structure for H2 is. The simplest molecule you'll ever draw. Two H's connected. I only have two things connected to each other. What's the only shape that that can adopt? I have two things connected. One thing and another thing, and I connect them. The only shape it can be is a straight line, right? It can't be anything more complex. The term that we use for a straight line is linear, right? So if you only have two atoms connected, it has to be a straight line. If we go back to the example that we drew of carbon dioxide, right? Carbon dioxide, CO2, has this as our Lewis structure, right? We had carbon and we had two lone pairs around it. So in order for those two double bonds to be as far apart from each other as possible, the best shape for them to adopt would be for those two double bonds to be in a straight line. Like so. If there's in any other orientation, right, the repulsion between them is going to be very, very, very large. So if I was the carbon in the middle, right, and this is my double bond here, right, to an oxygen, well then the other double bond would be exactly opposite to it in a straight line. That's the shape of CO2. It's linear or a straight line. If we take a look at something a little more complex, so here we have formaldehyde, which has the formula H2CO. If you go through and you draw the Lewis structure for formaldehyde, you'll see that it looks like this. Right, so here, the shape, and whenever we look at shape, the shape is always relative to the central atom. If you have that central atom with 3 electron groups around it, the only way for those 3 electron groups to minimize the repulsion would be for those 3 things to actually form sort of like a triangle, right? If any other arrangement, right, and you have a lot of repulsions between those electron groups. So the shape that adopts then is the shape known as trigonal planar, which is a flat shape. If we jump down, we're going to jump down here to a central atom that has 4 electron groups associated with it. And we looked at CH4 before, right? We actually drew the Lewis structure for CH4, and we drew it to look like this. Right, it's in your notes. We went through this one together. So here we have a central atom with 4 things around it. How does that look when you drew it on your page? It looks kind of flat, right? But the true shape of methane is anything but flat. It actually looks like a tripod with the head sticking out, with a carbon in the middle, and you have those 4 H's attached to it. So it's not flat, even though when you draw anything on a piece of paper, it looks flat. Right? It's important to keep in mind that there is going to be significant 3-dimensional nature associated with a lot of these molecules. So this shape actually that it adopts is known as tetrahedral. That's the fancy name that we give to that tripod with the head sticking out. All right, so I want to show you really quick before we end here for today a website that has a lot of these shapes and different things associated with them. So the website here is, I'll write it on the board, phet, P-H-E-T, .colorado.edu. All right, I know when you start drawing these molecules on a flat piece of paper, it's really difficult to visualize what they look like in 3 dimensions. So if you go on here, there are different simulations. So if I click on simulations and you scroll down, right, you'll actually see chemistry as one of them. So you click on it, and then there's an option on there for molecule shapes. Right, you click on it, you can run it directly from the website, and you can go in and you can move these things around. Right, so this here, for instance, is CH4. This is what CH4 looks like, methane. So there's your carbon in the middle. You can move it around, and you see it's not flat. Right, it actually looks like a tripod with a head sticking out from the top. And that shape, if you look down here, the geometry of this, or the shape, is called tetrahedral. Right, and there are a couple of other ones. You can look at your pull-down menu. There's several options. We looked at CO2, right, carbon dioxide. This is exactly what it looks like. It's a straight line, which means that it's linear.